This 14th chapter in Principles of Finance Openstax Regression examines the applications of correlation and analysis in the finance industry. Correlation analysis allows the determination of a statistical relationship between two numeric quantities. Regression analysis can be used to predict one quantity based on a second quantity, assuming there's a significant correlation between the two quantities. In finance, regression analysis is used to calculate the beta coefficient of a stock, which represents the volatility of the stock versus overall market volatility, with volatility being a measure of risk. In this discussion, the focus will be on analyzing the relationship between one dependent variable and one independent variable, where the relationship can be modeled using a linear equation. This is otherwise known as linear regression. Correlation analysis studies the relationship between bivariate data, which is data collected on two variables, where the data values are paired with one another. Correlation is the measure of association between two numeric variables. For example, you may be interested to know if there's a correlation between bond prices and interest rates, or between the age of a car and the value of the car. To investigate the correlation between two numeric quantities, the first step is to create a scatter plot that will graph the XY ordered pairs. The independent or explanatory quantity is labeled as the X variable, and the dependent or response quantity is labeled as the Y variable. To assess linear correlation, the graphical trend of the data points is examined on the scatter plot to determine if a straight line pattern exists. If a linear pattern exists, the correlation may indicate either a positive or a negative correlation. A positive correlation indicates the dependent variable increases. The dependent variable tends to increase as well, or as the independent variable decreases, the dependent variable tends to decrease. In other words, the two quantities move in the same direction. A negative correlation indicates that as the independent variable increases, the dependent variable decreases, or vice versa. In other words, the two quantities move in opposite directions. If there's no relationship or association between the two quantities, where one quantity changing doesn't affect the other quantity, you can conclude there's no correlation. When expecting a scatter plot, it may be difficult to assess the correlation based on a visual inspection of the graph alone. A more precise assessment of the correlation between the two quantities can be obtained by calculating a numeric correlation coefficient, otherwise known as the symbol R. The correlation coefficient is a measure of the strength and direction of the correlation between the independent variable x and the dependent variable y. The formula for R was shown in the previous slide. Excel or a statistical program like R is typically used to calculate the correlation coefficient. Note that N refers to the number of data pairs and the symbol sigma x indicates the sum of the x values. Once the value of R is calculated, this measurement provides two indicators of correlation: the strength of the relationship and the direction of the relationship. The value of R gives the following information. R is between -1 and +1 always. The size of the correlation R indicates the strength of the linear relationship between two variables. In other words, the closer you are to the absolute value of 1, that indicates a stronger relationship. If R is 0, there's no linear relationship or linear correlation. If R equals 1, that is perfect positive correlation. -1 means perfect negative correlation. In both of the perfect cases, all the original data points lie on a straight line. The sign of R gives the following information. A positive value of R means that when x increases, y tends to increase, and vice versa. A negative value of R means that when x increases, y decreases, and vice versa. An important step in the correlation analysis is to determine if the correlation is significant. By this, you're asking if the correlation is strong enough to allow meaningful predictions for y based on x. One method to test the significance of the correlation is to employ a hypothesis test. This lets you decide whether the value of the population correlation coefficient rho is close to 0 or significantly different from 0. This is decided based on the sample correlation R and the sample size N. If the test concludes that the correlation coefficient is significantly different from 0, the correlation coefficient is said to be significant. A quick shorthand way to test correlations is the relationship between the sample size and the correlation. If the absolute value of R is greater than or equal to 2 divided by the square root of n, being the sample size, then this implies that the correlation between the two variables demonstrates that a linear relationship exists and is statistically significant at the 5% level of significance. Or we're 95% confident there is a relationship. In addition to the measure of center, the measure of spread of variation in a data set is important. It's good practice to report both a measure of center and a measure of variation for a data set. The data values are concentrated close to the mean in some data sets. In others, the data values are more widely spread out. Measurements such as the standard deviation and variance are used to quantify the amount of variation in a data set. In linear regression analysis, the equation of straight line is written in a slightly different way using the model y hat equals A plus BX. B is the slope of the line, A is the y-intercept. Y hat is used to indicate a predicted value of the dependent variable y for a certain value of the independent variable x. If a line extends uphill from left to right, the slope is positive, and if the line extends downhill from left to right, the slope is negative. The first step in any regression is to create the scatter plot. Proceed to calculate the correlation coefficient R and check the significance. If you think the point shows a linear relationship, you would draw a line on the scatter plot. This line can be calculated through a process called linear regression. You only calculate a regression line if one of the variables helps to explain or predict the other variable. If x is the independent variable and y the dependent variable, you can use a regression line to predict y for a given value of x. When formulating the linear regression line of best fit to the points on the scatter plot, the mathematical analysis generates a linear equation where the sum of the squared residuals is minimized. This analysis is referred to as the method of the least squares. The result is that the analysis generates a linear equation that is the best fit to the points on the scatter plot, in the sense that the line minimizes the differences between the predicted values and observed values for y. The regression line equation that you calculate from the sample data gives the best fit line for this particular example. You want to use this best fit line for the sample as an estimate of the best fit line for the population. Examining the scatter plot and testing the significance of the correlation coefficient helps you determine if it's appropriate to do this. The assumptions underlying the significance test are: there's a relationship in the population that models the average value of y for varying values of x. The y values for any particular x value are normally distributed about the line. The standard deviations of the population y values about the line are equal for each value of x. The residual errors are mutually independent, meaning there's no pattern. The data are produced from a well-designed random sample or randomized experiment. Once the XY data is collected, and assuming the correlation between x and y is significant, you can generate the best fit line to model the relationship between the two numeric variables. Once this best fit linear equation has been developed, predictions can be made for specific values of the independent variable x. Once a correlation has been deemed significant, a linear regression model is developed. The goal in the regression analysis is to determine the coefficients a and b in the y hat equals a plus bx regression equation. The slope b and y-intercept can be calculated using the formulas that you see on the screen. These are cumbersome, especially for a significant number of data pairs. Technology is often used, such as Excel, a calculator, or statistical software, etc., to calculate these values. The slope of the line B describes how changes in the variables are related. It is important to interpret the slope of the line in the context of the situation represented by the data. The slope of the best fit line tells you how the dependent variable y changes for every 1 unit increase in the independent x variable on average. The intercept of the regression equation is the corresponding y value when x is 0. The intercept of the best fit line tells you the expected mean value of y in the case where the x variable is equal to 0. In many scenarios, however, it may not make sense to have the x variable equal 0, and in these cases, the intercept does not have any meaning in the context of the problem. Other times, the x value of 0 is outside the range of the x data that was collected. In this case, you should not assign any interpretation to the y-intercept. Regression analysis is used extensively in the finance industry. Typical applications involve determining if there's a correlation between various stock market indices like the S&P 500, the Dow Jones Industrial Average, and the Russell 2000 Index. Typical application of regression is to determine if the price of stock can be predicted based on some other quantity such as the stock market index. Another application is to investigate if there's a correlation between indices such as the Russell 2000 Index and the DJIA. Does the value of the Russell 2000 Index depend on the value of the DJIA? Is it possible to predict the value of the Russell 2000 Index for a certain value of the Dow Jones Industrial Average? We can explore these questions using regression analysis. Suppose you collect historical data for the Russell 2000 and the DJIA indices, and the correlation is deemed to be significant. Using the y hat equals a plus bx model, we get y hat equals negative 1,496.34 plus 0.11x. If the Dow Jones Industrial Average has reached a value of 32,000, we'll let x be that and substitute into the equation and calculate using the equation to predict a predicted value of negative 1,496.34 plus 0.11 times 32,000, yielding 2023.66. So we would predict that it's about 2024 when the DJIA has reached a value of 32,000. An important application of regression analysis is determining systematic risk for a particular stock, known as beta. This measures the volatility of the stock compared to a benchmark such as the S&P 500 index. If a stock has more volatility compared to the benchmark, the stock will have a beta greater than 1. If it has less volatility, Beta will be less than 1. Beta can be determined as the slope of the regression line when the stock returns are plotted versus the returns for the benchmark, like the S&P 500. A key aspect of generating the linear regression model is to use the model for predictions, provided the correlation is significant. Once a prediction is made for a certain value of the independent variable, it's useful to calculate a corresponding prediction interval to provide a form of confidence interval for the predicted value of the dependent variable. To generate predictions or forecasts using the linear regression model, substitute the value of the independent variable x in the regression equation and solve the equation for the dependent variable y. You can do this in Excel with the forecast command. To use the command, enter the value of the independent variable x, followed by the cell range for the y data and the cell range for the x data. Note when predicting values for y, it's generally recommended to only predict values for y using values of x that are in the original range of the data collection. One important value of an estimated regression equation is the ability to predict the effects of y on a change in one or more values of the independent variables. A prediction interval is a form of confidence interval for a predicted value of the dependent variable. In other words, you are asking for the estimate of the impact on the dependent variable y of a single experiment using a value x. That formula is given to you as you see on the screen there. Thanks for watching and listening. Be sure to like and subscribe.